Okay, so we are doing a 3-2. I told you guys yesterday we weren't, and that was a lie. So anyway, sorry about that. So we're going to go ahead and we're going to get through kind of 3-2, which is a fairly important lesson. So the key concepts, we're going to talk a lot about variation. So in your notes, we're working on standard deviation and variation. That'll be, and I'm guessing maybe that's probably a new concept for you. Is that true? Have you heard of variance or standard deviation outside of just kind of the talk about what it is?
I'm pretty sure we did standard deviation last year.
Okay. So it might be new to, or you might have some standard deviation. I'll show you the formula, and keep in mind, remember we are going to be using a stats crunch, which is a lot like kind of an Excel, but it'll allow you to do standard deviation and variation, mean, median, and mode, the central tendencies we had before, just through a computer program. But for Chapter 1, I'm going to limit that just a little bit. You won't be able to use StatCrunch just yet on your test. So I want you to do standard deviation the old way with a small data set, but then after that, I'm going to go ahead and allow you to do standard deviation from the computer. So let's go ahead and start off. Again, the range of the data sets we've talked about before, and range is going to be the minimum value and the minus the maximum value. That's a little different than we had for the mid-range. How did we do the mid-range before? Do you remember the difference between the two?
Yeah.
What was that? We took the lowest plus the highest and then to the average between the two. So the range is going to be just then the highest value minus the lowest value. That's also going to be standard deviation, and standard deviation are going to be a set of sample values, and it's denoted by S when it's going to be a sample, or it's the Greek letter for S for population, but it's a measure on how much the data deviates from the mean. So in other words, if I know that I have my data set, and we've talked about that with the histograms before, and we had the mean then would be right set in the middle. And so when we have the standard deviation, what it's telling you is how far away this data set is from the mean. And the population, if your graph looks a little bit flatter and doesn't have quite so much of a height to that, then you're going to then it'll affect your standard deviation. Let's go ahead and just show you kind of what I mean by some of the problems that we have. Now, a standard deviation is going to also, from the sample, is found by this formula. Remember, we talk about the sum of, and this is also going to be the x value. So this is your data point minus, this is going to be your mean. So you might want to, if you want to mark it, this is going to be the mean of your sample size. And then we're going to take all of those, we're going to square the difference between those two, and then we're going to add them all together, because that's what the sum of means. And then we're going to divide it by 2 and then take the square root of it. And so an alternate formula, which is derived from this one, is the one down here, but I'm going to actually just focus on this one because it's not that hard to go ahead and implement and do. We're also going to talk about kind of the properties of standard deviation. So standard deviation is a measure on how much the data deviates from the mean, which we talked about before. The value of the standard deviation is never going to be negative. So keep in mind, when you put this into your formula and you square it, when we have a difference, we might have a negative number when we take the data point minus the mean, but then you're going to square it, so that will make it always positive. And then we're going to divide it by, obviously, a positive number since it's n minus 1. And then when you take the square of it, it'll always be positive. So again, S is going to be, the standard deviation will never be negative. Larger values of S indicate a greater amount of variation. In other words, how far, that means that the graph is spread out a little further. Standard deviation S can also increase dramatically with one or more outliers. And remember, those outliers are going to be those points that, like if you had, when we did the dot plot, when we had, I think it was like 36, but then we had the next data point was in the 50s, and then we had a whole bunch of these other data points. And so the outliers are going to be either small values that kind of are different from the rest of them, or it could be even larger values. But they do dramatically increase your standard deviation. The units of standard deviation, such as minutes and feet and pounds, are the same as the units of the original data set. So, in other words, when I take and I find a standard deviation, if my data set is going to be pounds, that means my standard deviation will be so many pounds from the mean. And the sample deviation S is based on an estimator of the population of the standard deviation, which is the sigma, or the lowercase sigma, which is the Greek letter for S. And so, which means that the sample standard deviation do not center around the value of sigma. The average rule of thumb is a crude way for a simple tool of understanding and interpreting standard deviation. Okay, and so when I think about significantly low or significantly high values, then remember this is a value which means the mean, and that means that it's going to be minus 2 standard deviations or lower from the mean. And if I have something that's significantly high, then I'm also then 2 standard deviations above the mean, because again, it'll be a spread. It's how far out your data piece is going to be. So when I do the rule of thumb, okay, so when I talk the rule of thumb, remember it's just in estimating the standard deviation. And so if I have mean, which is going to be the very middle of that, then I'm talking about significantly low values, which will be 2 standard deviations lower than the mean, or significantly high values, which are 2 standard deviations above the mean. Okay, a population standard deviation is going to be represented by your sigma. Okay, and the different formula is used to calculate the population instead of dividing by 1 for the sample. So the difference here lies in that we divide it by n minus 1. Instead of this, we would just then do n. X still is going to represent the individual points. The mu right now is going to be your population mean. Remember on the other one with the S, we had it as an X bar. And then n is going to be your population size. All right. The variance of the standard values is a measure where variance equals the square of the standard deviation. So variance is considered S squared. And so when we look here, it would be from the formula, it would be before you take the square root of it. And the population variation is going to be, again, the sigma, or the Greek letter squared. And the notation for these, on your notes, I need you to take this little s off, and it needs to go in there. There should have been a return there, so it should say s squared equals the sample variation. So s is going to be the sample standard deviation, S squared would be the sample variance, and then again your sigma would be the population standard deviation, and then the Greek letter squared would be the population variance. Okay, on number 4. All right, so the importance of the variance. The variance, the units, are the squares of the units of the original data set. Okay, and then it's also, the variance is not going to be resistant. The value of the variance will also never be negative, and it goes back to that formula where we're squaring each of the potential negative values that we have. And it's only 0 when all the data values are the same number. And so in other words, which would be kind of odd, but if you had a data set that didn't have any change, but because your variance is basically defined as how far things are from the mean. And if they're all the same number, then obviously it could have a 0, but it would be very odd. The sample variation is an unbiased estimator of the population variance. So in other words, the difference between the two of the sample versus the population would be then just what we talked about in Unit 1, that the population would be the whole group, where a sample would be just a select few in those. So when to divide by -1 or n minus 1, there are only n minus 1 values that can be assigned without a constraint. With a given mean, we can use any numbers for the first n minus 1 values, but the last value will be automatically determined. With an n minus 1, the sample variance tend to center around the value of the population variance and within just the division of n. When we talk about, like when we started with the next graph, the page I have this a norm distribution curve. And so when you're dealing with the norm distribution curve, it's also signed as the bell-shaped distribution. You can also call it the 60, 95, 99.7 rule. And what it means is that 67 or 68% of all the values will fall within one standard deviation of the mean. Let me show you what I mean by this chart. So in this case, if I look at the chart that's on the next page, if I know my mean will always be dead center in the middle. Okay, and then if I go one standard deviation to the left or to the right, then I know that these two amounts will represent about 68% of my entire population. Okay, and that's also referred to as the empirical rule. Okay, if I keep going out to 2 standard deviations from the mean, in other words, I'm going to go out this far, then I know that these 4 summations, if I take 34.13 and 34.13, the 13.59 and the 13.59, that's going to add up to 95% of my entire population. And then the next one, if I keep going out to 3 standard deviations to the mean, this little shape right here represents the 2.14%. So just right here, there's just an amount. And that's going to represent 97.7% of my population. So obviously, if I say something that something is 3 standard or bigger than 3 standard deviations from the mean, then we're talking about it being in a very, very small percentage of our data point. In other words, it's less than 99%. It would be in the greater than 99 percentile. So it's a very small amount of our population. So here's the problems that we need to work. Now we pulled out some problems that same problems that we did yesterday with the 3.1, and so we have the NFL players from the Seattle Seahawks, and they have the weights of those listed. And so the very first thing we did yesterday was we wrote them in descending order. So we started off with 189, 190, 190, 195, and etc. Okay, we also found from section 3.1, we found the mean. So X bar is going to be then the 231.1 pounds. Okay, if I still, again, doing my range, which is a new amount, I'm going to take my highest amount minus my lowest amount. So my highest would be then 305, and then I'm going to subtract then that from the 189. And 305 minus 189 is going to be, by magically, 116 pounds. Okay, now let's go ahead and calculate the variance, and which is going to be s squared. Okay, so s squared, I don't have the radical, but I'm going to take the sum of x minus x of 1. So I'm going to take my first data point, which is going to be 189. I'm going to subtract my mean, which is going to be then the 231.1. But then at that point, this should be squared. I'm going to square that. Then I'm going to add then the next data point. So I'm going to go ahead and my next one will be 190. I'm going to subtract it from my mean of 231. And then I'm going to square it. And I'm going to keep going on that. So I have another one of 190. Minus the 231.1, expression squared. I'm going to keep going all the way until I get to the end of my data set. And while we're doing this kind of makes sense on why you would want to maybe utilize your technology, because the larger your data set, the more involved you're going to have to be. So I'm going to pull this down. So I have the 305, whoops, did I go with the wrong one? So we had 89, 90, 190, 190. This should be 195. 195. And then I'm going to have then a 202 minus 231.1, expression squared. I'm going to go plus 225 minus 231.1, expression squared. and I'm going to go then plus 235 minus 231.1 expression squared, and then plus 252 minus 231.1 expression squared. Continuing on, it'll be then 254 minus 231.1 expression squared, plus the last two, 305 minus 231.1 expression squared, and then plus 305 plus 231.1 expression squared. Now, all of this is over my entire data set, so n minus 1. And if I have a total of 11 values, then I'm going to take 11 minus 1. So 11 minus 1 would be then 10. All right, I didn't leave enough room. So let's go ahead and finish it out. I'm going to put it right here. You should, when you put that into your calculator, which I need to get mine. Should I go ahead and jump through the magic of my, I ended up with, as all of this, when I did them earlier, your answer should be 19,236.91 all over 10. And then obviously then I'm going to move that over one more decimal place. So since I'm dividing my 10, so my variance would be 1923.7 lbs. Okay, so after that, after I find this amount, then my standard deviation would be just the square root of this. So again, S is going to equal the square root of my variance, which would be then the square root of the 1923.7, which is going to equal 43.9 pounds lbs. All right, so again, data sets, that's how you'll find that. And then again, remember variance is going to be the squared, S, the standard deviation will be just the S. Can I have you go ahead and write down the answers and come back to them just so you got the numbers written down? Okay, perfect. Okay, so with the next one, we also talked about, which is a nice, this one, the next question, I like it because you have 8 data points rather than 11, which is nice. But again, it's the same question we had before, where we're talking about the amount of different hotels for one night at on the Las Vegas Boulevard Strip. So again, you'll start by writing them in ascending order, like we did before. You'll also find then your mean, and if you remember, we found our mean, it would be 171.3. And then my range again is going to be from my highest amount, which is going to be then the 264, minus my lowest amount. And so that'll be then a total of 187. So the variance, again, so just to have, so we get this, hopefully we'll start. So we're going to start off with x minus x bar. So in other words, my first piece would be then 77 minus, what will I subtract it? Bregan, do you know? What would I mean? So from that, remember we calculated mean earlier on section 3.1 to be 171.3. So your very first thing you're going to do is you're going to take the 177 minus then the 171.3. And then notice on this one I need to have a squared here, so you're going to square that. Okay. The next one, I'm going to go ahead and go plus then. My next data point would be 104 minus the 171.3, expression squared. Plus my next one would be the 121 minus the 171.3, expression squared. Plus the 153 minus 171.3, expression squared. And then plus the 195 minus 171.3, expression squared. I'm going to continue it. Plus then the 212 minus the 171.3, expression squared. plus the 264 minus the 171.3 expression squared. And all of this will be over what? Can you tell me that part?
7.
Yep, 7 divided by 7. So the magical answer here, I'm going to go ahead and just say so we can save some time. By calculating this before, I end up getting then, this would be then the 4,626.2. And then in order for me to find my standard deviation, then I would take then the square root of that. So the square root of 4,626.2 would be then the $68. So in a nutshell, what that means is on my data points, okay, I know my mean is going to be straight up and down. It's going to be the same as this is going to be the 171.3. And then for one standard deviation on each part from the right and the left will be the amount of $68. So in other words, if I add 171 plus 68, then that number would be then one standard deviation from the mean. If I take 171 minus 68, then that's going to be one standard deviation from the mean to the left. The next part, you're given some of the values. And so let's look at the number 2. The females have a pulse rate which has a mean of 74 beats per minute and a standard deviation of 12.5 beats per minute. Is the pulse rate at 44 beats per minute significantly low or significantly high? And so the range, using the rule of thumb to identify the limit separating the value as significantly high or low. So let's go ahead and look. First of all, to identify my graph, this means that my mean, which is right in the middle, showing that I have 50% on the left hand or the right hand side and 50% of the left hand side, is going to be the value of 74 beats. Okay, so that's where this line indicates. Okay. So then if I think about in terms of like 2 standard deviations from the mean, I'm going to come out one standard deviation and I'm going to have then 12.5. And so this amount right here would be then the 74 plus my standard deviation of 12.5. And so this number here has to be then 86.5. If I come over here one standard deviation to the left, then that would be 74 minus then the 12.5. And so this number here would be then 61.5. Now if I keep going and I go another minus 12, so if I go a minus 12.5, then I'm 2 standard deviations from the left, which is going to be 49 beats per minute. Remember I had the 86.5. If I also add the 12.5, that means this number here has to be 99 beats per minute, is 2 standard deviation from the mean. So when I look at this, my significantly low values are going to be less than, if I go the mean minus 2 standard deviations, remember that was the 49 beats per minute. 2 standard deviations above that was 99. So the question is the pulse rate of 44, okay, so the question, 44 beats then is what? Is that significantly low?
Yes.
Yes, you're right, because it's less than the 49. It's even more over here. So the answer is yes. Okay, on the next one, if I said a number like 100 beats per minute, I would also say yes, that is significantly high because that's over the 2 standard deviations. Okay, how clear is that? Clear as mud? All right.